Okay, well, just to recap, our Markov matrices is a matrix where the columns add up to 1. And so we have V1, our vectors are state vectors. This is all in this section on migration matrices, which are examples of Markov matrices. And so we're starting with 200 people at location 1, no one at location 2, and this tells us how they change the diagonal entries to the people that stay in the same place. So that half the people of 200 stay at location 1, half go to location 2. The second step V2 equals M times V1, which equals going to be 1/2 times 100 is 50 plus 1/4 of 100, which is 25. And then location 2 is going to be 1/2 of 100 will be 50 plus 3/4 of 100, 75. So this equals 75, 125. Okay, so now it started off with 200 people at location 1 in the middle. The first step was 100, 100. Now it's to 175, 125. Okay, so if we wanted to know V to the n, right, that would be M to the n times V0. Well, that's, and we would hope that there'd be a long time limit. That there's what would be the limit, the pattern as n goes to infinity. Okay, well, so but that's a matter of that's going to be a matter of finding m to the n. There's also there's going to be a simpler, there's actually going to be a way to find an approximate answer for this that's going to be easier than finding okay, well, let's go on. So this, therefore we have a matrix M here, and we have a matrix M which equals 1/2, 1/2, 1/4, 3/4, and we want to find m to the n. So that means that we need to do this whole procedure of finding the eigenvalues and stuff like that. And since the entries have, let's see. Since the entries here are fractions, that's a good reason for doing it in. So we're going to have here a 2x2 matrix, and we'll call it M sub I for migration. And this will be 1/2, 1/2, 1/4, 3/4. Okay. Now, so we want to find eigenvalues and eigenvectors. So let's look at the eigenvalues. So the eigenvalues are 1 and 1/4. Now it turns out that for a Markov matrix, there's a theorem that says the largest eigenvalue is always the number 1. So this is an illustration of a general procedure that for this is a Markov matrix, and the largest eigenvalue is going to be 1. And here's another one, it's 1/4. These eigenvalues don't have to, these ones down here don't have to be, I'm not even sure if they have to be real, but they're going to be, maybe they might be, but they could be negative. So they might not be, the other eigenvalues may be a little weird. Okay. So, but there's two, so then that makes it simple. We can go through and find the eigenvectors of the right matrix, MI, okay, and there they are. So then we can form, let's do V for the migration matrix. And that will be 1/4. Okay, and then we need inner matrix 2 by 2 for P. Okay, and we're going here, we have this one here. The first one, 1, 2, reading off 1 and 1 minus 1. Okay, so there's P, which is, I've taken the eigenvectors that correspond to the eigenvalues and made the matrix P. Then we want to invert that matrix. We can say P inverse, and we have to change the percent's the one before, so you don't want to sort of put the explicit form in if you do have to do something twice. It'll be the same. Okay, so there's P inverse, and we can check just for fun that it actually is the identity matrix, but we then want to see, well, we want to see the nth power to 2 by 2. This will be d to the nth. And it's going to be 1, because 1, the first item is 1 to the n is 1, but this one will, the second one will be 1/4 to the nth power. Okay, so there's 1/4 to the nth power. And so then we want to find, I believe, let's get it the right way around.
So d to the n matrix, since that's the d to the n matrix.
Yeah, d to the n is the diagonal matrix to the nth power, which we can construct explicitly. And I want to get so here we want P times d to the nth times P. Let's see, what is it? P is that one, P inverse, okay. Okay. So it is, I think this should be m to the nth. Now, it's a little bit hard to read, but I'll write it down here at the bottom. Okay, we use Wx maxima to find, let's heaven is not always on top, okay? So m to the nth, why is that? Let's make this always on top. Okay. M to the nth equals, this is going to be 1/3 plus, whoa, this is weird. Oh, I see the problem. I want to only have this one available. No. Okay, I guess I shouldn't do that. It's going to, if you look at this, this is 2/3 times 4 to the n. So this is 2/3 times 4 to the n. It's not 34 to the n. Okay? This one is 1/3 minus 1/3 times 1/4 to the n. And this is 2/3 minus 2/3 4 to the n, and 2/3 plus 1/3 1/4 to the n. Okay. So, well, now.
1/3 times 1/4.
Oh, what? Excuse me.
Is it 1/3 times 1/4?
Yes, it's 1/4 times 1/4 to the end. So it's like this. Maybe I should write this one differently. This is 2/3 times 1/4 to the n, and this one is minus 2/3 times 1/4 to the n. Okay. Now the question is, what happened? This has a nice limit when n goes to infinity. See, this is 1/4 to the n. Well, that's like 1/4 squared, 1/4 cubed. The second term here is getting smaller and smaller and smaller. So what it turns out is that m to the n large is approximately equal to 1/3, 1/3, 2/3, 2/3. Okay? Now, what that means is that v to the n, the large state limit is going to be m to the nth times v0, which equals 1/3, 1/3, 2/3, 2/3 times, say, 200, 0. We start with 200 people. Then, as we can just do this by hand, well, more or less, it's going to be, well, let's just, so I don't have to think about it, 200 times divided by 200 divided by 3 is great. So we have to toggle numeric output, do this again, and it's, so that's pretty clear. It's going to be 66 and 2/3. And the bottom one here is going to be twice that, right? It's going to be 2 times, it's going to be 133 and 1/3. So that's going to be 199 plus 1. So it actually adds, despite the fractions here, because you can see the exact fractions, this is going to be, it adds to 200. Okay. And if you wanted to know the frequency, so that you can see, if you wanted to know the frequencies, you would take, you would just take out, you would divide by the 200, right? So that would actually just be here, frequencies of 1/200 times this vector would be 2/3, 1/3. I got this backwards. Yeah, I've got it. I wrote it the wrong way around. The top one is 1/3. Is, oh, it's not that. It's the, yeah, it's the other way around. Sorry about that. It's 1/3, 2/3. So if you start from, no matter what you start with, you're going to end up in the large scale limit with 1/3 of the people being at location 1 and 2/3 at location 2. Those fractions were obvious because you had like 1/2, 1/4, 3/4. So that there's, anyway, so this is just a real trivial case that you can see how you could get get information with a large scale limit of migration matrices, and how you can use this whole eigenvector thing. Now, there is, however, another way to think about this, which is, well, let's save that for maybe next week. It goes through and does this. It does it with a 3x3 example. And there's some examples in the text, I think, that it shows you the same, it goes through and shows you this same, the same procedure. But however, here you could just use WX maxima to find like v to the 10th, and that's going to be close to the final value. You can also use the same, interpret the same situation, interpret those numbers as probabilities, and interpret as a random walk. Someone like instead of like a frequency of organisms going back and forth, you can think of one organism starting at location 1 and find the probability after n steps of being at location 1 or location 2. So it's the same, it's a different interpretation, but it's the same idea here. And so your initial values, instead of being a big number, are going to be ones. Like this is a person starts at 1 and they have a certain, and you want to find a long time, probably after in this particular matrix here, after 1 time step, the probability is 4 tenths, 2 tenths at their different locations. It keeps changing. Okay, and here's sort of the thing. Every markup matrix has 1 as an eigenvalue. Okay, so what you can do is, let's see. You can go through and find this. What you want to, okay, here's maybe the story that one can tell. Let's say that you had a matrix M and its largest eigenvalue was 1, and all the other ones were less than 1, right? Well, let's say that your matrix M acts on some initial state that you divide into, but the initial state, because the eigenvectors for a basis for the set of all states. So you can say any state is going to be a certain fraction in eigenstate 1, a certain fraction eigenstate 2, a certain fraction eigenstate 3, and so on. Let's just do 3 things here. So now, if we act on this with M to the with M, right? Let's say we act this M to the n, to we want the large scale limit. Let me do it first with 1, so you can see without that complication. Well, if I multiply this in, this is going to be A times M times V1 plus B times M times V2 plus C times M times V3, okay? Now then, since these are eigenvectors, this is going to equal A times lambda 1 V1 plus B times lambda 2 V2 plus C times lambda 3 V3. Okay. Now, if I act with M to the n on this same vector, that's just going to equal A times lambda 1 to the n V1 plus B times lambda 2 to the n plus C times lambda 3 to the n V3, okay? Now, if this is a Markov matrix and lambda 1 is the largest eigenvalue, which is 1, this is just equal to, basically, it's equal to A times V1 plus B times lambda 2 to the n V2 plus C times lambda 3 to the n V3. But these numbers here, lambda 2 and lambda 3 are less than 1. So if they're like a fourth or a half, no matter how big, I keep multiplying, they get smaller and smaller and smaller. Well, so as m gets really, really large, m to the n is approximately equal to A times V1, the largest eigenvector. So to find the steady state behavior of a Markov matrix, all I need to do is find the eigenvector of the largest eigenvalue, which is 1. So I just take the matrix, subtract 1 from the diagonal entries, and find the largest eigenvector. That's a linear system, right? So finding that one eigenvector then tells you what this long-term steady state system is. This becomes exact, it then goes to infinity. And the examples here show you that if you go up to n equals 10 or just a relatively small number, you're almost all the way there to infinity, so to speak. It's like there's sort of point of diminishing returns, and so this is a nice way to subvert the whole process of it works it works for Markov matrices because of the special feature, and it works. You don't have to do all the stuff with eigenvectors and eigenvalues. But anyway, that's sort of a nice thing. You can see I've given out of revisions here. Okay. That is those two things. That sort of tells the story of Markov matrices with two applications of migration matrices and random walks. And there's lots of other examples of Markov matrices, like you might have like speech recognition problems or like speech translation problems. You want to write a program that will produce the written transcript of someone speaking. And the problem is with that is that you need if you get something like 90% accuracy, that's really bad because of the fact that that means you have words all over the place that have been misrecognized, and someone has to go through laboriously and fix that. So you need to sort of up the game there with that. Anyways, that's a whole technology for which Markov matrices can be relevant, and they're relevant all over the place. They're relevant for banks that want to deter insurance companies that want to determine risks, because they have to do any place where you have many situations to account for and probabilities. You can model them and model the risks of loans, the risks of all kinds of stuff with Markov matrices. Anyway, so there's another application, which is dynamic systems, which uses exactly the same technology. Okay, basically it's the same idea that you have your states are vectors. And matrices move the state to next state. Okay, so it's basically sort of the same pattern as the migration matrix, but you don't have the restrictions. They don't have to be Markov matrices. So usually, for example, you have something like this in which you have a recursion relation, or you have a recurrence relation in which it says, okay, I've got a state xn here, xn, yn, and I've got a matrix here, 2, -3, 1, 4, that changes it to the next state. And I can ask then, what happens in a long term? So this is a definition of a dynamical system. It's, see, I have a discrete linear system like this, right? And you can see here that I've got a discrete linear system in which I can express, this is a recurrence relation in which x to the n, y to the n is mapped by this matrix to the next state. And again, you can see that the n+1 state is p d to the n, p inverse v naught, so for where the matrix A that's transporting you is going up there. So it's the same procedure of looking at the power of a matrix using eigenvectors and a similar matrix. Okay, here's an example of where you give a dynamical system, it goes through, finds the eigenvectors D, finds the state, and you find that this is the final state, and you then, if you go to infinity, it has this pattern. Another one is the Fibonacci sequence of numbers, which is, you can see here, this is a two-step relation because of this one. You can convert this into a two-step dynamical system of defining x to the n-1 as y, and then saying y to the n+1, which is this one. So this relation becomes the second row, and you're making a sort of a definition of the first row. Well, apart from this sort of maneuver, you end up then converting the Fibonacci sequence into a matrix that transports you from one set of numbers to the next. And then this matrix here, the Fibonacci matrix, has the eigenvalues, 1/2 1 plus the square root of 5, 1/2 1 minus the square root of 5. And here's the eigenvectors. So you can write then the diagonal entries, you can write P. And you get eventually, if you go P to the inverse and do everything out, you get this formula for the nth Fibonacci number. So it's like a complicated formula, but it's like what in here is sort of that golden ratio of something like 1 plus the square root of 5. Anyway, the point is you've got a thing that is complicated, and you can get a closed form solution for the Fibonacci numbers. And it turns out this is an integer, despite all the square roots of 5 and stuff. So that's the kind of thing you can do. And then here's some problems, like the another similar to the Fibonacci sequence. And then here's another one, dynamical system here. And that's basically but that's basically all the same thing, right? It's just 3 different examples of using dynamical systems are used in different contexts for different things. And that will lead us, I think, to one of the things we'll do next week, which is we can apply this stuff to models of epidemics and stuff, and see how epidemiologists where linear algebra comes when you model epidemics, and see how and you'll see some of the numbers and stuff that come up, and this is one of the simplest epidemiology models from the 1920s is the SIR model. And so we'll look at that model and and it's the simplest one. I mean, it's only got 2 variables or something, essentially, but then the ones that actual epidemiologists use can have, 10, 20 variables. So they're dealing with 10 by 10 or 20 by 20 matrices or linear algebra that's like fairly complicated.
So I guess my question is the current demonstration that's happening this weekend, is it going to include
No.
topics on this?
The current demonstration, let me show you that, since that'll be also relevant, that it doesn't have any of this stuff on it. So there are some regex exercises, including a couple on the epidemiology thing that are fairly simple, but there's no questions on a demonstration this weekend. I can show you the topics on it so you can be prepared. Okay, so here is demonstration 3 topics. Maps to matrices. Okay, you have map to matrices 2, matrix to map. Okay, basis action to matrix, lengths and angles, orthogonalization, matrix and map properties, vectors and areas, eigenvalues and eigenvectors, eigenvalues and eigenvectors. This is a 2 by 2 case, this is a 3 by 3 case. So the only stuff you need to be able to do is to find eigenvectors and eigenvalues. So it goes back a ways because we haven't had, covers the material that goes back about matrices and stuff like that. So, and lengths. So this is like the last, so there's no determinants on it. Okay, and then the other thing is that there are 2, open up, there'll be 2 exercise sets in formatively named problems 1 through 7. And so each of these exercise sets are optional, and they just allow you to, if you have a missing exercise set from previous if you look here at your progress page, and you'll see that over here with the exercises, these count I think 20% of the grade, and that there's two here that will, so if you have two that are missing here, that at least these X's mean that they're dropped. The two low scores are dropped. And the same thing for the well, okay. The same thing for here. If any of these are offered, when these are offered, they'll only be what you're seeing here is ones that are in my system, but that aren't visible to you. So when one of these comes up, there'll only be one of these that you will have. That only one of your scores will count. Like here for demonstration 3. Well, let me see. What have you done? I have to make sure this works for. Okay.
There was like 5 minutes. Can we just quickly review the maps matrices?
Sure.
You were talking about concepts, and I realized I'm not super.
Okay. So let's do. Okay. So let me save this. It is the 27th. Okay. And let me